Welcome back. In this video, I will explain the attention by coding the encoder part described in the Attention is All You Need paper. In the next video, we'll cover the decoder part. While there are efficient implementations of these algorithms that are faster and better optimized, for the purpose of learning, I will sticking to use only NumPy. Here is the timeline of what we'll be doing, and you can skip to any section you prefer. First, we'll build a vocabulary of tokens from the documents we've extracted from the internet. We'll also create sequences of tokens to feed into our encoder networks. Next, we'll generate token embeddings for our vocabulary and calculate the corresponding positional embeddings. Finally, we'll pass these vectors through various components of the network, including multi-head attention. First, I use code from previous video to extract articles from Wikipedia, which results in a JSON file containing the document text. Next, we'll write a function to process these documents and break them down into tokens. These can be characters, words, or sequences of words. I'll create a class called Tokenizer. In its init method, I'll pass the location of the article's JSON file. Then I'll write a method called initiateVocabs that takes the JSON file location as input. In this function, we'll create a dictionary named vocabulary and update it with 3 special tokens: start of sentence, end of sentence, and padding. Each token will have an assigned index and its frequency in the document. Now I'll open the JSON file and iterate through each article. I extract the body text, to separate the text into sentence. I'll split the document using the period. For each sentence, I'll first increment the frequency of the start of the sentence token. Then I'll break the sentence into individual tokens, including the period as part of the tokens. Next, for each token, I'll check if it already exists in our vocabulary. If it does, I'll increase its frequency by 1. If not, I'll add the token to the vocabulary and update the index counter for the next word. Let's create an instance of the Tokenizer class and check the vocabulary. As you can see, we now have a simple vocabulary where we know each word's index and its frequency. For example, the token other appears 5 times in our document. Now let's create sequences of tokens to use as input for our encoder. We want each sequence to have same length. Therefore, I'll define sequence length in the init method and compare the token length with this value. Therefore, if number of tokens is more, we trim the tokens to fit the fixed length. And if it is shorter, I'll pad it accordingly. Now let's create sequences of tokens to use as input for our encoder. I'll start by creating a list called training sequences. As we iterate through each sentence, we'll create an empty list to store the token. First, I'll append the index for the start of the sentence token. Then, for each token, I'll append its corresponding index from the vocabulary. Finally, I'll add the padding token index and the end of sentence token. I set the tokenizer sequence length to 128. As you can see, the first element in the list represents the tokens in the first sentence of the document, where each token is represented by its index in the vocabulary. To verify this, we can convert the indices back to the tokens by creating a dictionary that maps indices to words, essentially the inverse of our vocabulary. I'll extract each word from the first sentence and print it. The length of the sentence is 128 tokens, as it's padded to the fixed length. At this point, we've successfully created a vocabulary and sequences to feed into the transformer encoder. For the next step, let's create an embedding matrix for the tokens in our vocabulary. The goal is to map each word to an n-dimensional vector, which I'll refer to as embedding dim. I'll add embedding dim to the inputs of the init method Then I'll write a function called initiateEmbedding To implement this, we'll call the resulting matrix a vocab embedding. Using NumPy, I'll create a random array with the shape of number of tokens in the vocabulary by embedding dimension. In transformers, it is crucial to create positional embeddings to indicate the position of each token within a sentence. Unlike RNNs, which process tokens sequentially and capture positional information, transformers process tokens in parallel. As a result, they lack any knowledge of the order of tokens. To address this, we introduce positional encodings, which are designed to have the same dimensionality as the word embeddings. This ensures that the positional encodings can be summed with the word embeddings, allowing the model to incorporate positional information. According to the paper, we use sine and cosine functions with different frequencies to calculate the positional embeddings. Here, pos represent the position of the token in the sentence, and ith is one element in the positional embeddings. For even indexed items, we use the sine function, while for odd indexed, we use the cosine. Now let's implement this in our method positional embedding. First, we'll create a zero matrix with a shape of sequence length by embedding dimension. Then we'll iterate through each token. For each index in our embedding dimension, we apply the sine function for even indices and the cosine function for odd indices. Finally, we update the positional vector with the calculated values and return it. Now I'll create an instance of the tokenizer, and let's assume we want to map each token to a 256 dimensional vector. Let's check the number of tokens in our vocabulary. We have 321 unique tokens in our vocabulary. This means that the vocabulary embedding matrix has a shape of 321 by 256. Indicating that we represent each token with 256 values. Additionally, our positional vector has a shape of 128 by 256, where 128 refers to the length of our input sequences for the encoder. Using matplotlib, let's visualize the positional embeddings. The graph displays the values of the positional embeddings for each position in the input sequence across the embedding dimensions. The color intensity in the graph indicates the magnitude of the positional embedding values. For example, if you pick a row corresponding to the first token in the sentence, it shows the values of the positional embeddings for that token across all 256 dimensions. Up to this point, we have successfully created our vocabulary along with its corresponding embedding vector and positional embedding vector. Now we are ready to pass these vectors to the encoder. I will create a separate class named transformer. In this class, I will pass an instance of the tokenizer, allowing us to access the vocabulary embeddings and other essential attributes. Let's implement the multi-head attention mechanism. I will create a method called attention sequence and passing it the training sequence we have built. The training sequence consists of a sentence converted to token indices. And for each token index, we'll retrieve its corresponding embedding vector from the vocabulary embeddings and then add the positional encoding. For future calculation, I will ignore the batch dimension to simplify the process and make it easier to understand. Now let's discuss the attention model. In one attention head, we create 3 copies of our sequence embedding matrix. We then transform these matrices using linear transformation to obtain 3 vectors: query, key, and value. For multi-head attention, this operation is performed n times, where n is the number of attention heads. As a result, we have n sets of q, k, and v vectors. I will add the n parameter to the init method. I will initialize each vector with the shape n by sequence length by head dimension. Head dimension specifies that the output dimension for each vector should be the embedding dimension divided by n. For example, if we have a 256-dimensional embedding, splitting it into 4 heads will yield a dimension of 64 for each vector. Next, I need a matrix for transforming the embedding vectors into a new space. To accomplish this, I will write a separate function to initialize weights for each transformation head. For instance, let's assume we have 3 copies of an embedding vector with the shape of 128 by 256. To transform this vector to a shape of 128 by 64, we need a transformation matrix with a shape of 256 by 64. Therefore, I will create these matrices randomly Now, for each head, I will multiply the embeddings by their respective transformation matrices to obtain K, Q, and V. To give a sense of what the query and key vectors represent, consider each token's Q vector as a way of expressing what it seeks from the surrounding tokens. For instance, in the sentence, "The chef cooked a delicious meal," the Q vector for the token chef might indicate a search for other tokens that are related to cooking, such as cooked or delicious. Conversely, the keys represent the actual attributes of each token, acting as an answer to the potential queries from other tokens. It is like each word saying, "Here is what I represent." For example, the key vector for cooked would contain features like it is an action indicating something done by a subject and likely to be linked with a subject, chef, and an object, meal. When there is a strong connection between two tokens, it appears as a high dot product between their q and k vectors. For example, if the q vector for chef aligns well with the k vector for cooked, this suggests that the chef is actively engaged in the action of cooking. To compute this dot product between the keys and queries, I will perform matrix multiplication between the keys and queries, which I refer to as scores. The score matrix is a square matrix with a shape of sequence length by sequence length, with each entry corresponding to the score for a specific pair of tokens. I divide the scores by the square root of the embedding dimension before passing them through the softmax function. This scaling helps prevent large values in the input of softmax, which could lead to low gradient values during updates. After applying softmax, we obtain a square matrix with values ranging between 0 and 1, which indicates the strength of connections between token pairs. Here we see the scores for this sentence, and we ignore special tokens. We can see higher values for related tokens and also the pair of similar tokens. Next, we multiply this score matrix by the value matrix. Values represent the actual content or meaning of each token. They carry the information that needs to be passed along. So, once attention scores are calculated, values are weighted by these scores to provide the final information we want to propagate during the attention process. This results in a new matrix with dimensions sequence length by 64. Let's implement the softmax function, which essentially computes the exponential of each element and divides each of these exponential by the sum of all exponentials. To prevent overflow issues, we first subtract the maximum value from all elements. This adjustment does not alter the output because of the properties of the exponential function. To combine the outputs from each head, I will use concatenation along the last dimension. We should apply a linear transformation to merge and combine the information gathered from each head. I initialize another variable called wout with the shape of embedding dimension by embedding dimension. After this linear transformation, we have a new matrix with the same shape of sequence length by embedding dimension. Additionally, the paper employs dropout layers before the skip connections, which I will implement here with a dropout rate of 10%. So if the dropout rate is 0, we simply return the input. Otherwise, we create a mask by sampling from a binomial distribution where the probability of getting 1 is 1 minus rate, and the probability of getting a 0 is rate. We then multiply this mask by the input. To maintain the scale of the output, we also divide by 1 minus rate. After applying the dropout layer, we add the initial embeddings to have an updated embedding matrix. We also normalize the result using layer normalization. To normalize, we first calculate the mean and a standard deviation of the input. The output is then computed by subtracting the mean from the input and dividing it by its standard deviation. Next, we pass the normalized output to a feed-forward network. According to the paper, this network consists of two dense layers, the first with 2048 units and the second with a size equal to embedding dimension. I will define a method called feedforward that takes the input, initial weights, and biases as parameters. In our weight initialization method, we will set up the weights and biases. For the feedforward computation, we return the results of multiplying the input by the weights, adding the biases, and applying a ReLU activation function. Following this, I apply another dropout layer. Finally, we add the input to the output of the feed-forward network, normalize this result, and obtain the final output of the encoder. Let's go through an example. We create a tokenizer with a sequence length of 128 and an embedding dimension of 256. For the transformer, we pass the tokenizer and the number of attention heads. There are some typing errors. I will try to fix them. We then feed the first training sequence into the transformer's attention sequence function. Here I should add the positional embedding to sequence embeddings, which I will fix it now. So let's break down each step. So the weight matrices are shaped as number of heads by embedding dimension by 64. When we multiply the embedding vector by these matrices, we obtain outputs for the keys, values, and queries, each with the shape of sequence length by 64. We then calculate the scores by multiplying the key matrix with the transpose of the query matrix. This results in a matrix with dimensions sequence length by sequence length, which reflects the relationship between tokens in the input sequence. Next, we multiply the score matrix by the value matrix to generate the output of a single attention head, which has dimensions of sequence length by 64. We concatenate the outputs of the 4 attention heads, resulting in a matrix with dimensions sequence length by embedding dimension. This concatenated output is passed through a linear transformation to combine each head outputs. The transformed output then enters the first layer of a feed-forward network consisting of 2048 units, followed by a second layer that matches the embedding dimension. Finally, we add a skip connection resulting in a matrix with dimensions sequence length by embedding dimension. The output of the encoder serves as a rich representation of the input sequence, encapsulating the contextual relationships between words. This encoded representation can be utilized for various applications such as machine translation, sentiment analysis, and other NLP tasks. So thank you for watching. See you in the next part where we will implement the decoder part of the transformer.